Okay, so in today's class we will continue with stream ciphers. So yesterday you have seen some small examples to understand that stream cipher. The problem was I was interested in reconstructing the stream cipher. That is, given the sequence, can I again reconstruct the corresponding LFSR? Okay. So in today's class we will essentially talk about two topics. We will discuss about linear complexity. I think I started with this and I will continue with this, and mainly we will concentrate on this algorithm that is called Barley-Massey algorithm, which is used to solve this problem. Okay, it is a very phenomenal and seminal paper, so we will discuss on this, and it is quite important. So I hope you understand why we are studying this, because suppose consider a very simple stream cipher. What you do is that you essentially have got a key stream k, for example. Okay, and what you are doing is, suppose consider that you are just taking mi and obtaining the corresponding ciphertext ci, right. So you know that in context to models like, for example, chosen plaintext or known plaintext models, where you know the corresponding value of mi and you know the corresponding value of ci, you know the value of k, right. But the point is that given this value of k, can you also know the corresponding initial secret key with which it started. So this is the key stream, right, not the actual key. So there is an internal algorithm here, and there is an input secret key which is being provided as an input, right. So there is a secret k or key which is the actual secret of the cipher. Okay. So therefore the observer is essentially observing at this point, and from there he is interested in constructing the LFSR and also the key. So we are considering a single LFSR system, okay, and trying to understand that whether a single LFSR system which has actually got nice pseudo random properties can actually be reconstructed. Okay. So Barley-Massey algorithm. So if you remember the problem, that is, I can essentially decompose or rather write all these key bits as linear combinations of the internal secrets, right. And how many secret values are there? There, for an n length LFSR, there are actually 2n secrets, because you do not know the initial seed, okay, that gives you n bits. You also do not know the corresponding connection polynomial, okay. And another thing which you do not know is the length of the LFSR, right. So therefore you will find that you can actually write them as a system of linear equations and you can solve them, but this is an unwieldy process, okay. And Barley-Massey algorithm gives a very simple and elegant technique in order to solve this problem. Okay. So we will with this motivation we will study this problem, and so first of all, this is a recap of at the LFSR structure. So you see that you have got Sj minus 1 to Sj minus L. Okay. So please pay attention, because there are certain amount of formalisms required to understand the basic principle of the algorithm. Okay. So there is some amount of involved mathematics. So therefore Sj minus 1, Sj minus 2 to Sj minus L plus 1 and Sj minus L. So how many lengths are, how many flops are there? There are L flip flops, right, or L storage elements. So the corresponding feedback Sj you get as a linear combination of these points, but thing is that whether you are taking the feedback or not, that depends upon a control bit. Okay. So there are also L control bits here. So you see that you take this and you multiply with this corresponding feedback and you exert that with the previous things, right. So this is a very simple structure of the LFSR. So the LFSR was said to generate a finite sequence, say S0, S1 to Sn minus 1, when this sequence coincides with the first n output digits of the LFSR. Okay. So then we say that the sequence is being generated by the corresponding LFSR. Okay. Now you note that if L is greater than or equal to n, that is, if the length is quite larger compared to the length or the sequence that you want to generate, then generating is trivial, right. You can just simply stream in the data and you can obtain the corresponding output. But the problem becomes when L is smaller than n, that is, the sequence is a larger sequence, right. So we will be concentrating on this part of the problem, that is when L is smaller than n. So it follows that the LFSR generates the sequence if and only if this is true. Okay. So why have we started from j equal to L? So you note that what to read out this particular equation, it says that Sj is equal to the sigma of Ci multiplied with Sj minus I, okay, and your j starts from L. Why? Now, because before that you have just streamed in the data, right. So, therefore, that is, I mean, the feedback effect does not come for the previous before this j equal to L point, right. So, the problem starts when only when j is equal to L, and after that this has to be a linear combination of the previous L values. Okay. So, this is a very important equation which we have to keep in mind, that is S j is equal to sigma I equal to 1 to L C I S of j minus I. So, simply to remember, it is just the coefficients multiplied with the previous L states of the L values of the LFSR. Okay. So, first of all, let us consider this theorem. It says that if some LFSR of length L generates the sequence S0 to Sn minus 1, but not the sequence S0 to Sn minus 1 and Sn. So, I have added one more value to this sequence, then any LFSR that generates the latter sequence, if it has got length of L dash, then you can actually prove that L dash is greater than equal to n plus 1 minus L. Okay. So, if you remember the previous last day we were doing a simple example, right, where we saw that till some point you are easily able to construct the LFSR. Okay. But the point starts when you are going beyond that. Okay. See, for example, if I start with a 0, if you remember the previous day's example, we started with 0 0, right. So, 0 0 you can do with a 0 length LFSR. Okay. So, when you are doing from 0 0 1, then immediately your length jumps to 3, right. So, then you require a 3 stage LFSR. Okay. So, this is exactly the same thing. It says that so this was a trivial example where you see that in this case, in the particular example that I am talking about, your value of n is actually equal to n plus 1 is actually equal to 3, because n was equal to 2 and L was equal to 0. Okay. So, actually, although I have said you that L dash is greater than equal to n plus 1 minus L. So, therefore, we okay, first of all let us try to prove this result, that is L dash is greater than equal to n plus 1 minus L. Okay. So, in order to prove that, you observe one thing from this theorem statement itself, that is n minus L plus 1, right. So, you can write this as n minus L plus 1. So, what happens when n is smaller than L? This is actually trivially true, right. The length has to be greater than equal to 0. Okay. But the problem we will be essentially therefore considering when n is actually greater than equal to L. Okay. So, when n is greater than equal to L, that is the interesting problem. Okay. So, let us in that case, first of all we will start with contradiction. So, let us contradict this statement. So, if I contradict this statement, that means L dash greater than equal to n plus 1 minus L, I am contradicting. So, therefore, what I am assuming that L dash, let L dash be less than n plus 1 minus L. So, therefore, L dash is less than equal to n minus L. Okay. So, I can write this as L dash is less than equal to n minus L. Okay. So, this is by contradiction, we have just contradicted the statement of the theorem. Okay. And what we will see that is that if this is true, then we end up with something which is wrong, that is we are violating the initial starting point. Okay. So, what are the starting points? Let us see this. So, this is what I have said to you already, that is the case 1, that is L greater than equal to n, the theorem is trivially true. For case 2, so let us consider two LFSRs. Okay. So, the two LFSRs has got say for example, C1 to CL and C1 dash to CL dash. Okay. So, these are the corresponding coefficients of the two LFSRs. Okay. So, you note that we have assumed that L dash is less than equal to n minus L. Okay. That is by contradicting the theorem statement. Okay. So, now this is clear, that is this corresponding polynomial LFSR, the first LFSR has generated the sequence till n minus 1, right. So, therefore, I can write this equality, but this is not equal to Sn. Why? Because it is not generating the corresponding Sn value, right. that is the n plus 1th value in the sequence. Okay. So, but this LFSR is generating all the values. So, therefore, you start from L dash and continue till n, this equality holds, right. So, therefore, these two equations are clear to us, right. This is a simple statement of where we started with, right, that is the initial theorem statement basically. So, this LFSR is generating till n minus 1 values, but this one is generating till the nth point, okay, then is nth value, but this one is not generating the nth value. So, therefore, this inequality. Okay. Is it okay? Yes. Okay. So, now let us start considering this particular value. Okay. So, you see that what we will do essentially is this, that is you start with the first LFSR coefficients, that is consider sigma C I S n minus I. Okay. So, therefore, what I am doing is that I am calculating this particular value when j is equal to n. Okay. So, I am trying to evaluate this, and I will show that if this is true, okay, and if this is true, then this is actually equal to S n. Okay. So, therefore, that contradicts my initial starting point, right. Do you understand the idea? So, therefore, so we will try to prove this. Okay. So, how do I start to prove this? You can see that sigma, if I just write sigma I mean if I just write sigma I equal to 1 to L C I S n minus I, okay, then we can actually substitute this value. Okay. So, that is what we do. So, why can we substitute this value? Do you understand this? Because in order to substitute, you note one thing, that this has to lie in the range of j, because otherwise this definition does not hold, right. So, therefore, you see that here you consider this particular sequence, this says the sigma I equal to 1 to L C I of S n minus I. Okay. And you note one thing, that from what are the two extreme ends of this sequence in that case, in this corresponding sigma value? It starts with S n minus 1 and continues till S n minus L, right. And what we have assumed is that n minus L, if you come here, n minus L is actually greater than equal to L dash, right. N minus L is actually greater than equal to L dash, right. So, therefore, if that is so, then this particular sequence, that is S n minus 1 to S n minus L, is actually a subset of S L dash to S n minus 1. Why? Now, because L dash is actually smaller than n minus L, right. So, this is essentially a subset of this particular sequence. You see that? Yes. You see that if I consider this sequence say from S L dash to S n minus 1, then L dash, because I have contradicted, L dash was less than equal to n minus L, right. So, therefore, this is actually a smaller value compared to S n minus L, right. So, therefore, this is a bigger sequence compared to this. Okay. So, therefore, this is a sub part of this. So, therefore, this for all the values of S n minus I, where I runs from 1 to L, I can substitute the second equation. Okay. I can write them in terms of the coefficients of the second LFSR, right. So, therefore, that is exactly what I do. I take this S n minus I and I substitute by this value. So, you see that this is equal to sigma k equal to 1 to L dash C k dash S n minus I minus k. Okay. So, therefore, this follows straight away from this equation, right. So, you see that if I am interested in computing S n minus I, okay, then I will substitute here instead of j, I will write here n minus I. So, this becomes equal to sigma C k dash S n minus I minus k, right. So, therefore, that is exactly you can substitute here, it becomes equal to C k dash S n minus I minus k, right. Till this part is clear. So, now what you can do is that you can interchange these two sigma values. Okay. So, you can bring this one here and bring this one here, and also because of this particular fact, I mean again you have got this. So, if you consider the next sigma, it is C I Sn minus I minus k. Okay. So, this I can use the previous equation, that is the this particular equation, okay, and I can again instead of this I can write Sn minus k. Okay. Now, note that you can again write this because of this fact, that is now Sn minus L dash till Sn minus 1 is a subset of Sl to Sn minus 1, because L dash is less than equal to n minus L. Okay. So, therefore, if you write this, now you see that what you have essentially obtained here is nothing but equal to Sn. Okay. So, therefore, what you are essentially contradicting is the initial starting point, that is the first LFSR cannot generate the Sn digit. Okay. So, therefore, where did we go wrong? We essentially assumed this which was wrong. Okay. So, therefore, if we this proves the theorem, that is L dash is actually not less than equal to n minus L, but it is actually greater than equal to n minus L plus 1, okay, or n plus 1 minus L, right. Do you understand the principle? I mean, you can always go back and look at the proof in details, but this is the idea. The idea is that if there is a particular LFSR which is unable to generate sequences from S0 to Sn, I mean which generates a sequence from S0 to Sn minus 1, but not Sn, then you need to add on to that length. Okay. So, therefore, if you add on to that length and the length becomes say L dash and the previous length was L, then there is a definite relation between L dash and L, okay, and that is what we proved in this theorem. Okay. So, therefore, now you can actually better understand the linear complexity problem. Okay. So, what is the linear complexity problem? This is what I define, is that this is the minimum length of all the LFSRs which generates the sequence S0 to Sn minus 1, right. So, clearly you can see that ln S will be less than equal to n. Why? Yeah. So, therefore, if I am considering S0 to Sn minus 1, any n bit LFSR can definitely generate it, right. The problem is, can I obtain lesser than that, right. So, another thing you note that moreover ln S must be monotonically decreasing, actually this will be monotonically non decreasing. Okay. So, there is a mistake, it will be monotonically non decreasing with increasing value of n. So, I think this also you understand this. Okay. So, therefore, so moreover ln S must be actually monotonically non decreasing with increasing n. Okay. So, why it is true? Because you are also understand why it is true, because this will straight away contradict the initial hypothesis, right. So, we will start with certain conventions. The conventions are that the all 0 sequence is generated by the LFSR whose length is 0. Okay. So, you know that we are trying to develop a recursive construction. So, there are always some initial starting points for any recursive algorithm, right. So, these are the starting points, that is all 0 sequence is generated by the LFSR whose length is L equal to 0, okay, and if S0 to Sn minus 1 are all 0, okay, and your Sn is equal to 1, then the length which is required is actually equal to n plus 1, right. This we saw for our example, right. If you remember 0 0 1, 0 0 could have been generated by a 0 length LFSR, but 0 0 1 was generated by a 3 stage LFSR, right. So, therefore, this is what it says exactly, okay, and you can actually so these are the conventions. So, we will assume these as conventions. Okay. So, now let us consider another lemma. So, lemma is this, that if some LFSR of length L generates the sequence S0 to Sn minus 1, but not the sequence S0 to Sn minus 1 Sn, that is essentially you see that this Sn is not being generated, then you can actually show that the linear complexity for n plus 1, okay, for this sequence is actually greater than max of ln S or n plus 1 minus ln S. So, this is actually quite trivial. This follows from the previous idea, that is we know that it is monotonic and therefore ln plus 1 s has to be greater than or equal to ln s. We also proved this result. So, it has to be greater than the maximum of these two, right. So, therefore, it is either greater than or equal to the maximum of this or maximum, whichever is the maximum value, it has to be greater than that, right. So, ln plus 1 s has to be actually greater than or equal to maximum of ln s comma n plus 1 minus ln s. Okay. So, this is an interesting lemma which will help us to recursively compute the linear complexity, okay, right. So, you note one thing, that is, when do you require an updating, that is, you can understand that if ln s is, if n plus 1 minus ln s is actually greater than ln s, then you require to add on to the length, right. And when this happen, when will this happen? When n plus 1 minus ln s is greater than ln s, right. So, therefore, if I write this, it will look like this, right, that is n plus 1 minus ln s, okay, is greater than ln s. So, that means that n plus 1 is greater than 2 ln s, right. So, I can write this as n is greater than equal to 2 ln s, right. So, rest of the cases updating is not required, that is, when n is less than 2 ln s, then updating is actually not necessary. So, the length gets updated only, it can get depending upon certain cases, that is, if there is, I will define something when it gets updated, but whenever there is an update, the update will happen only when n is actually greater than equal to 2 ln s, right. Do you understand why? Because of the monotonicity again, right. Yeah. So, now we are actually more or less staged to understand the Baldacchia-Massey algorithm. So, it is a recursive algorithm which produces one of the LFSRs of length ln s, that is minimum length, ln s is the minimum length which generates the sequence, which generates the sequence S0, S1 to Sn minus 1 for any integer value of n. Okay. So, for this again let us look back at the connection polynomial. So, you had C d equal to 1 plus C 1 d plus so on till C l d power l. Okay. So, this was my connection polynomial which has degree at most l in the indeterminate in this case is d, in the variable d. Okay. So, the convention is that second area starting convention, it follows from the previous thing, that is C d is equal to 1 for the LFSR of length l equal to 0. Okay. So, if length l equal to 0, then we will assume that C d is equal to 1. Okay. So, this is just a convention. Okay. So, therefore, for a given sequence S, I will write that C n d is equal to 1 plus C 1 n d plus so on till C ln s n d to the power of ln s. Okay. So, this is just a rewriting of the previous connection polynomial. Only thing is that I have specified that the length is actually equal to ln s, and all these sequences, if you note carefully, are actually denoted like C1, C2 and so on till CLN s, but there is also a at the top I have written a suffix, values to indicate that this is a generator of the sequence till S n minus 1. Okay. That is from S0 to Sn minus 1. Okay. So, therefore, this LFSR essentially generates the sequence S0, S1 so on till Sn minus 1. Okay. So, what we are interested in calculating in that case, Cn plus 1d, right. So, what we are interested in calculating the value of Cn plus 1d, because Cn plus 1d will also give us the corresponding coefficients, right, which will generate the sequence S0, S1 to Sn, right. So, now you see that before going into the next things, we will try to understand certain things, that is, we will try to prove a recursive construction of this particular polynomial, okay, that is C n d, and at the same time we will also show that the lemma 1 that we stated, we showed we essentially till now have proved an inequality, right. That is the ln s was, that is ln plus 1 s was actually greater than equal to the maximum of ln s or n plus 1 minus ln s. Okay. So, actually that greater than equal to should be replaced by an equality. Okay. That is, it will be an equality instead of a greater than equal to. Okay. In order to prove that, so we will essentially develop a proof which merges these two proofs. Okay. So, we will prove that equality by induction, okay, and at the same time we will give a proposal for a polynomial which will be a candidate for Cn plus 1d. Okay. So, therefore, this is a constructive way of proving. Okay. This is not an existential proof, but a constructive proof. Okay. So, we will not only prove the existence, but we will also show you how it is constructed, right. So, therefore, in order to do that, we will define something which is called a discrepancy, which we have already seen. Why? Now, if you remember the previous example, with a simple example that we started with, we were able to calculate the values till a particular point, right. Like for example, if you remember, we had 0 0 1 1, right. So, you know that 0 0 1 can be quite trivially constructed. How? Now, you can just take 3 stage LFSR and you can just write the feedback. I mean, the feedback polynomial could be simply a shift register like this, right. So, you can take 0 0 and 1 and you can stream out this value of 0 0 1, right. So, what is the corresponding polynomial here? C d is equal to 1 plus d cube, right. But the moment you see that you consider this particular one, what is the next thing that you get fed back? It is actually a 0, right. When you want a 1 here, you are actually getting a, with this particular LFSR, you are getting back 0. So, that means there is a discrepancy. Okay. That is the idea of discrepancy. Okay. So, what you are actually getting back and what you want, and an XOR between that two. Okay. So, here the moment you see that you actually get back 1 and what you get back is 0 and what you want is 1, you know that you have to make certain modifications in this structure. Okay. So, you note that I will just do a simple modification, I will introduce an XOR here and take this feedback. Okay. So, in that case, this LFSR will generate the sequence 0 0 1 and 1. If you remember the previous thing what we did, I mean we actually solved this and found this, right. So, you see that you get 0 0 1, that is quite trivial, but the next thing is the XOR between 0 and 1. So, you get back 1, till this point it is fine. So, what is the updated polynomial now? C d. So, if I write this in terms of my C n d, this was C 3 d, but this is C 4 d. So, what is C 4 d here? 1 plus d cube, right. So, therefore, you see that you are able to construct the corresponding polynomial, but because when you are doing this algorithm, you will take care of the fact that there is a discrepancy at this point and accordingly modify the polynomial. Okay. And when there is no discrepancy, then there is no modification required, you can just go ahead with the previous polynomial, right, previous construction of the LFSR. Yeah. Yeah, it will be 1 0 0. Yeah, I am streaming out from this point. Yeah. So, it will be 0 here and 1 here, but anyway, I mean the rest of the discussion holds. Okay. So, I am getting back first 0 0 and then 1, right, that is true. So, therefore, you see that whenever there is a discrepancy introduced here, then only you require to modify this polynomial, right. So, now you come to this particular definition of discrepancy. It says that lemma 1 is actually an equality, and we have seen this for the base case, but we will prove it for the further cases using induction. Okay. Why have I said it holds for the base case? Because I have already proved you that for a 0 0 1 sequence, that was exactly equal to 3. Okay. Because you started with L equal to 0 and then it was actually equal to n plus 1, minus 0. So, it was actually equal to n plus 1. Okay. So, for the base case the equality holds, for the rest of the cases we will prove it by induction. So, our hypothesis would be that this holds for ln s, okay, and we will try to prove this for ln plus 1 s. Okay. So, therefore, the corresponding polynomial is in this case C n d, okay, and this is what is the phenomenon which is occurring when you need an update. Okay. So, when do you need an update? When this S j XOR with what you actually obtain back, this is what you want and this is what you obtain. If you take an XOR, you get 0 for all the cases till n minus 1, but for j equal to n you get a non-zero value. So, you get a 1 here. Okay. So, this dn is called the next discrepancy, okay, and you need an update only when dn is equal to 1. Okay. So, therefore, you see that this is the discrepancy between Sn and the n plus 1s first bit, which is generated by the minimal length LFSR, which we have found to generate the first n bits of S. Okay. So, therefore, you understand the idea behind discrepancy, right. So, this is the difference, that is the XOR between what you actually obtain and what you wish to obtain, right. So, therefore, when dn equal to 0, then the LFSR also generates the first n plus 1 bit, and therefore, there is nothing to be done. So, ln plus 1 s is equal to ln s, the linear complexity remains the same, Cn plus 1 d also remains the same as that of Cn d. Okay. Problem happens when dn is equal to 1, then you need a correction of this discrepancy, right. So, you note one thing, that is so in order to do that, we will consider the sequence length before the last change. Okay. So, therefore, let us m be the sequence length before the last length change in the minimal length register. So, therefore, before this, whichever was the last change when you did for the length, that is, so m is a variable which is the sequence length before the last length change in the minimal length register. Therefore, last time when you change the length, okay, what was the sequence length, that value is being held by the variable m. Okay. So, you note that this is a recursive algorithm, right. So, you are keeping on updating one after the other, right. So, you are modifying the length sometimes, you are not modifying the length sometimes, right. So, therefore, when was the last time, so you go back, so therefore, suppose you are maintaining this as in the form of a table, you go back and see when is the last time when you changed the value of length, okay, and find out that what was the corresponding sequence length, right. So, that is suppose m. So, immediately you can understand that these two things hold, that is LMS is less than LNS, right, because of monotonicity, okay, and Lm plus 1s is actually equal to LNS, right, because you have updated your m value to satisfy this, right. So, this was the last change of, m is a sequence, right, but this is the length. Okay. So, you have, so what I have told you is that you have changed the length. So, which means that you have gone from m to m plus 1, right. So, therefore, LNS must be greater than LMS because it was the last change, m is the greatest integer before the last change. Okay. m is a sequence actually. So, LMS is the corresponding length of the LFSR, and Lm plus 1s must be equal to LNS, right, because this is the length that you are talking about. So, therefore, since a length change was required, okay, so you see that only at j equal to m there must be a discrepancy, but otherwise this would have been held fine, right. Therefore, the discrepancy was 0 in all these cases. Okay. So, therefore, since a length change was required, this LFSR, that is LMS, and with the corresponding polynomial, this will be a capital. Okay. So, CMD, this could not generate the sequence from S0 to Sm, right, and that is why you change the length, right. So, what is the sequence length here? M plus 1, right. So, in order to generate the m plus 1th sequence, length sequence, you had made a change in the value of m, right. So, therefore, immediately you can understand that the corresponding discrepancy for all these values till m minus 1 was equal to 0, but when j was equal to m, the discrepancy was a non-zero value. Okay. Now, by induction hypothesis, you can understand that Lm plus 1s is equal to lns, this we have already discussed. Now, by induction hypothesis, lns is actually equal to max of Lms and m plus 1 minus lnms. Okay. So, you can apply this, okay. And you note that lms is actually less than lns, and therefore, I mean rather this is no, this q is something which is generated by this software. So, this is actually a since. Okay. So, since lms is less than lns, so therefore, lns is actually equal to m plus 1 minus lms. Okay. So, lns is actually m plus 1 minus lms. Okay. So, now please remember this value till this point, that is lns was equal to m plus 1 minus lms. Okay. So, after this we will give you a proposal for the next candidate, that is till now we have assumed that we know CND and we would like to find out Cn plus 1d which generates the sequence till Sn, right, till Sn. Okay. So, this is the corresponding construction. The claim is that if you XOR CND with CMD which is multiplied by d to the power of n minus m, okay, this is the valid next choice for Cn plus 1d. So, you see that you have taken this and XORed with this. Okay. So, you see that the idea of this XORing is to correct the corresponding discrepancy value. Okay. So, at the point of your problem, this gives you a discrepancy, this also gives you a discrepancy, and both these discrepancies actually cancel each other. Okay. That is the idea. But let us little bit understand more closely to understand this phenomenon. So, you note one thing, that what is the degree of CD? The degree of CD would be the maximum of this degree. So, what is the degree of this? lns, and what is the degree of this? lms, but n minus m is multiplied. So, it is n minus m plus lms, right. So, note that n minus m plus lms can be actually written equal to n plus 1 minus lns. Why? Now, because of the previous equality that we found out, that lns, if you remember the previous equality, lns was equal to m plus 1 minus lms. So, if you substitute this value here, you obtain this. Okay. So, therefore, CD is actually an allowable connection polynomial, because you see that your maximum length is inside this. Okay. So, you see that now only one thing remains to prove, that CD does the correction. Okay. Because if CD does the correction, then what you have proved is that the length, that is the next length, is actually equal to maximum of lns and n plus 1 minus lns. So, you have proved that ln plus 1s is actually equal to maximum of lns comma n plus 1 minus lns, and therefore, the induction gets proved. Okay. We get the proof by induction, but till now we have actually not proved one thing, that CD actually does the correction. Okay. So, therefore, what we now need to prove is that CD does the correction, which means it generates the sequence digit Sn, okay, and at the same time does not disturb the previous sequences, right. So, in order to understand this, let us observe the value of CND. Okay. So, what was CND equal to? It was equal to 1 XORed with C1 n d, okay, this is a small c, plus so on till C lns n d to the power of lns. Okay. And what was CMD equal to? 1 plus C1 dash, okay, or you can just write 1 plus C1 m, okay, 1 plus C1 m d plus till C lms m d to the power of lms. Okay. So, now if you multiply this with d power of n minus m CMD, then what do you obtain? You just multiply this, right. So, therefore, it is d to the power of n minus m plus C1 m. What does this d become? N minus m plus 1 plus C LMS m d to the power of LMS plus n minus m, right. So, you note this equation and you note this equation. Okay. So, your CD is an XOR between these two polynomials, right. So, CD was my, by my definition, CD was CND XORed with d to the power of n minus m C of MD, right. So, now I can write I can enumerate all the corresponding coefficients for CD in terms of these two coefficients, right. So, how can I write? The coefficients will be correspondingly C1 will be equal to C1n, okay, and so on till Cn minus m. So, Cn minus m will be Cn minus mn XORed with 1, because you will have the correspondingly this particular term will give you a coefficient of 1, right, and so on. You can write Cn minus m plus 1, this will be equal to Cn minus m plus 1 n XORed with C1 m, right. So, subsequently you will have till this particular point again. So therefore, you understand that after a point there will be an XOR, right. So, now you note that if I need to find out the corresponding discrepancy value, okay, so therefore, I shall be interested in computing this value, right, Sj XORed with Ci Sj minus 1 sigma, where I runs from 1 to L, right. I need to ensure that this is actually equal to 0 for j running from L to n for all the values, right. So, you note that I can now write this as two separate parts, okay, because if you remember, if I write this, the corresponding coefficient Ci, that is these coefficients, I can write as an XOR of this XORed with this, okay. So, therefore, this gives you the first part, okay, and this gives you the second part, okay. So, therefore, if I am interested in computing Sj XORed with Ci Sj minus I, where I runs from say 1 to L, okay, then this will be equal to Sj XORed with sigma Cin Sj minus I, okay. This is one part, and the other part will be the corresponding part from Sj minus n plus m, okay, plus the other part of the sigma. So, what is the other part of the sigma? So, I hope you have understood why I am writing j minus n plus m, because at this point I am writing out the corresponding coefficient for Cn minus m, okay. So, Cn minus m is this, okay, and the corresponding seed value for this will be j minus n plus j minus n minus m, right. So, that is exactly this value, okay. So, therefore, the rest part of the sigma comes in. You have got Ci m, okay, and S j minus n plus m minus I comes in after that, okay. And you note that this I will run from 1 to LMS, and this will run from 1 to LNS, okay. So, you note that for all the previous values, that is for j running from L to n minus 1, this value will be 0, because you know that this LFSR was properly generating all these values, okay. But what about this? So, you see that the suffix here is j minus n plus m, okay. So, when your j runs from L to n minus 1, okay, j runs from L to n minus 1. So, you see that if you substitute here n minus 1, then you get n minus 1 minus n plus m. So, that is m minus 1, okay. So, therefore, this sequence is actually generating the first m digits of the sequence, okay, of its corresponding LFSR. So, therefore, this was actually properly generating. So, therefore, this value is also a 0 value. So, this is a 0 and this is a 0. So, you get 0 for j running from L to n minus 1. Okay. And what about when j equal to n? This will generate a 1 because of the discrepancy, and this will also generate a 1 because of the discrepancy, and both the discrepancies will get cancelled out. Okay. And therefore, you see that this corresponding, I mean, therefore, we say that the corresponding coefficient C D actually generates the entire sequence S n plus 1. Okay. So, this is not so trivial proof. So, therefore, please go back and look at the proof again and try to work with some small examples. Okay. So, the conclusions are that the LFSR with length L and connection polynomial C D generates the sequence S0 to Sn, and since L satisfies lemma 1 with equality, the induction also gets proved. Okay. So, you saw that L was actually equal to lns comma the maximum of lns comma n plus 1 minus lns. Okay. So, therefore, you are proving the equality also for ln plus 1s. Okay. So, I am not going into the details of the algorithm, which you can follow from this discussion. Okay. You must note one thing, that what you are doing is that you are maintaining some temporary variables like BD and M and things like that. M I have already defined. So, BD is another temporary variable and TD is another temporary variable, and you note that whenever there is a D equal to 1, so you are calculating the discrepancy. Whenever this D is equal to 1, then you are doing certain operations. Okay. And when do you require to modify the length? When L is less than equal to n by 2. I described to you why it is so, and only at that particular time you require to update the value of L, otherwise the L is fine. Okay. So, you can work through the details of this thing, but I will give you some examples, but I will tell you one thing, that until unless you work with your hand, you will not be so clear. Okay. So, therefore, please go back and work with some toy examples. Okay. So, consider the sequence of periodicity 20. So, therefore, this is for example, a sequence. You can actually plot the variation of the linear complexity with n by calculating this using the Baldacchio-Massey algorithm. Okay. And this is actually called the linear profile. So, you can actually plot them and it will look like this. Okay. So, you see that if this is the line corresponding to L equal to n by 2, then whenever L is less than equal to n by 2, the modification has taken place. Otherwise, when L is actually greater than n by 2, the modification is of L is not required. You get the step function at those places. Okay. So, you can little bit look it more closely to obtain certain interesting properties, but I will conclude with the example with which I started. So, therefore, this is the sequence, right. Yesterday we saw that a 4 step LFSR was unable to generate this sequence. So, in order to solve the problem, let us apply the Baldacchio-Massey algorithm. Okay. So, in order to do that, we will store that in the form of a table like this. So, you see that Sn, D, TD, CD, L, M, BD and N are some variables that is there, and we will start populating this table. Okay. So, this is the sequence which you wish to generate from 0 0 1 1 1 0 1 1. Okay. So, you start with a value of CD equal to 1, that was my convention, and your L value was 0. Okay. And BD, I mean M is actually in this case you start with initialize with minus 1, and BD is the corresponding polynomial which generates this sequence. Okay. So, this was my CMD in my discussion, okay, in the analysis. So, n is equal to 0 means till now you have generated till 0, okay, that is you have generated nothing until this point. Okay. This is just a initialization of the algorithm. Okay. So, what you do next is that you get 0, you know that what is the discrepancy, it is 0, right. So, therefore, you do not require to do any other thing. So, therefore, you see that all the things are kept intact. Okay. Next what you get is again a 0, again you have a discrepancy of 0 and therefore, you do not do anything, but the next thing you get a 1 is a 1, right. The moment you get a 1, your discrepancy is equal to 1, because you feeding back 0 and you are getting and you want 1, right. So, therefore, the XOR is 1. So, therefore, you know that you require to update the corresponding value of CD, right. So, you see that what you do is that you XOR the previous value of CD, that is 1, with the corresponding value of BD, but you multiply that with d to the power of n minus m. Okay. So, what is your n here? 2, and your m value is minus 1. So, 2 minus 1 is 2 plus 1 3. So, you get 1 plus d cube. So, you see that 1 plus d cube which has a length of 3 should be able to generate this particular sequence 0 0 1, and this we have already seen, right, with our hand exercise, right. So, therefore, what is the value of m equal to 2? So, m is the previous sequence before the length got changed. So, the length got changed here from 0 to 3, and what you have generated previously was till 2, right. So, therefore, m is actually equal to the previous value. So, therefore, in this case it is 2 and the corresponding polynomial was 1, and now you have generated till 3, that is the I mean 0 1 2 3, right. So, the next thing which you get is 1, and you again find that you have a discrepancy here, which means that you need to change the value of 1 plus d plus, I mean you need to change the value of C d. Okay. So, what you do is that you take n and you see that this is m. So, therefore, 3 minus 2 is 1. So, you multiply this with, so therefore, you take 1 plus d cube and you also XOR the previous value of b d, but multiplying that with d. So, therefore, you get 1 plus d cube, right. So, you get 1 plus d cube and your length. So, you see that you are not updating the length. Can you tell me why? Yeah, because of that inequality, right. So, therefore, in this case you do not require to update this value, okay, and therefore, you go ahead with this. So, you have generated till this point. So, therefore, you see that it works fine here for these things because it generates the discrepancy of 0. So, therefore, there is no other updating required for these stages, but at this point we were unable to construct with a 3-bit LFSR, okay. And you see that the discrepancy is in this case 1. Why? Now, because 1 plus d cube. So, if you XOR the previous this value and this value, that is the previous sequence values, you get 1 and 1 XORed, you are actually feeding back 0, but what you want is a 1, okay. So, what is the discrepancy value? It is equal to 1, right. So, therefore, you need to modify the value of C d. So, therefore, you take 1 plus d cube and XOR that with the previous value of b d, okay. So, so you get to, so therefore, what is the previous value of b d? It is equal to 1 multiplied with d to the power of 7 minus 2. So, that is d to the power of 5. So, you take 1 plus d cube plus d to the power of 5 and you get L equal to 5. So, you see that you have modified the length again, because 3 is actually smaller than 7 by 2. Okay. So, therefore, you have modified the value of this to 5, and therefore, you see that a 5-stage LFSR with this particular polynomial is able to generate the entire sequence. Okay. So, therefore, you see that using Baldacq-Massey algorithm you are able to calculate the corresponding minimal length of the LFSR, which will generate the sequence and also find out the corresponding polynomial. Okay. And actually, you can see from the algorithm statement the complexity of this algorithm is O n square. Okay. So, therefore, this is a quadratic algorithm to generate the corresponding sequence. Okay. So, this is quite efficient in that case. So, the references that I have followed are as follows. So, these are standard references, but I will suggest you to go back and read this paper. It is freely downloadable. It is called Shift Register Synthesis and BCH Decoding. Just concentrate on the first part of this paper. Okay. This gives you a description, but this actually talks in prime fields, and I have generalized this proof for GF2. Okay. I mean not generalized, made it more specific actually. Okay. So, this is a classic paper, it is IEEE transaction and information theory paper, but you understand. So, what we have learned from this example is that a single LFSR system is not good, right. If you have a single LFSR based stream cipher, then you can actually do a known plain text attack, you can obtain the key stream, and from there you can actually reconstruct the LFSR, you can know everything about the LFSR. Okay. So, given 2n bit sequence, you can construct the entire thing, right. So, therefore, you need a multi LFSR system. Okay. So, therefore, in the future classes, next day classes, we will concentrate, we will still continue with stream ciphers, and we will try to understand more detailed, I mean better constructions of stream ciphers using LFSRs and also not LFSRs.